Welcome, this is Mr. TG. This is section or lesson 9.3 from Algebra 2B. Today we're going to be exploring geometric sequences. First of all, let's define what a geometric sequence is. As you can see, as you look at your notes, you can see a geometric sequence is a sequence for which the ratio between consecutive terms is constant. This ratio is called the common ratio. Essentially, what we're talking about here is when you have a sequence of numbers, and if you're forced to multiply by a number to get the next number in line, then you have what we call a geometric sequence. That number that you multiply by is called the common ratio. In this case, the common ratio is 5. If you multiply 3 times 5, you get 15. 15 times 5, you get 75, etc. Now, the way you would make a sequence go down in value is you have a common ratio of a fraction. In this case, if we compare the first two to the last two, our common ratio is 1/2. You simply multiply by 1/2 each time to get the next fraction in line. If you can't come up with it just by looking at it, you can divide the second term by the first term, and that will give you your 1/2. 3/2 divided by 3 is going to be, well, let's just show you. If I did it without a calculator, this is how I would do it. 3/2 divided by 3 is the same thing when we multiply by the reciprocal, 3 over 1. We're going to multiply 3 times over 2 times 1 over 3. 3's cancel out, and we end up with 1/2. So if you're not very good with fractions and you cannot see what the common ratio is, that's a strategy you can use. Up here, I could have used it and just divided 15 by 3 to get my 5 if I needed to do that. So that's how you calculate the common ratio. Now, as you can see here, we've got two formulas again that we're going to be coming up with, the recursive formula and the explicit formula. And in these formulas, first thing with a recursive, you should write this in: a sub 1 equals your first term. You always have to make sure you establish that with the recursive formula, so don't forget to do that. With the explicit formula, we're not required to do that because we're comparing our value in our sequence to the term that we're on. R is what we're calling the common ratio. So what I want you to do at this time is see if you can just use the recursive formula formats here and come up with the recursive formula for problems 1 and 2. When you're done with that, you hit pause, work them out, come back, and I'll have them completed for you, and then we'll compare answers to make sure that you can create what we call the recursive formula for these geometric sequences. So hit pause right now and come up with those two. Thank you. Okay, welcome back. In front of you, you see I've set up the recursive formulas for each of these geometric sequences. Just a couple things that I've experienced kids make mistakes is one thing with recursive formulas. Make sure you do this. Don't forget to always represent the first term, because we're looking at the previous term to generate the next term in line. And it's just simply, this again represents our previous term. If I'm looking at 375, that would be the 75. And we're always taking it times 5, the previous term, to get the next term in line. The same is true with number 2. A sub n equals a sub n minus 1, previous term times 1/2, given the fact that a sub 1 is 3. And I should point out again that this number right here is the term that you're on. It's a subscript. A sub 1 just simply represents the first term. Now take some time here and set up the explicit formula for these two ratios using this formula. Thank you. Okay, welcome back. As you can see in front of you, I've created explicit formulas for each of these sequences, these geometric sequences. Again, n represents the term that you're on, not the actual value. Again, let's check it, see if it works. We put 1 in. Well, first, let's show you how we got these. You're taking the formula. This is the first term, which is 3. The r is the common ratio, which is 5. So it's real simple. All you need to do is replace those two, and then you have your formula. If I put the first term in for n, I get 5 to the 0 power, which by definition is 1 times 3 is 3. If I put the second term in, that's 2 minus 1 is 1. 5 to the first power is 5 times 3 is 15. And it continues to work for us. So this, again, will help us find any term in our sequence just given the term that you would like, and we don't have to list every single term. So it gives us the ability to find, let's say, the 50th term if we need to. Now, moving on down, we're done with geometric sequences. Now, I want to show you a problem where we're applying it to a 3x5 photo. What I'd like to have you do is enlarge that photo by 30%, 5 times, and ask what are the dimensions of the final enlarged photo. So try this on your own, and when you come back, I'll have it completed. Okay, welcome back. This is what I did when I enlarged my photos. First of all, I mapped it out for you. You can see our 3 inches here becomes something much larger. You know, if we're going to multiply by 1.3, which is a 30% enlargement. And by the way, if you're wondering how I got that, I changed the 30% to 0.3, and this is very similar to our exponential growth problems. You need to add 1 on, and I think you realize since it's getting larger, we're going to have a growth. So the 1.3, that's where that came from. And then as you can see, you know, we're going to increase by a product of 1.3 each time, which is a geometric sequence. Using my formula, explicit formula, I put in 1.3, which was my common ratio. I put in the starting value 3 and carried it to the 5th power, which is the common ratio. And we get a width of about 11.14 inches. Doing the same thing with my 5-inch length, I put 1.3 in as my exponential growth value, and we end up 5 as my term that I'm on. We end up with 18.56 inches. So you can see by setting up the explicit formula, it looks very similar to exponential growth and also decay models. Now with geometric sequences, we have what we call a geometric mean of the 2 numbers, and we can find geometric mean by simply using this formula. So to demonstrate that, all you would do, if they give you a geometric sequence here, 4 and then something in the middle and 12, you simply do this. You take the product of the 2 numbers, 4 and 12, you multiply them together, and then square root that result. 4 times 12 is 48. Square root that result, and you end up with the value that's between. That's the geometric mean of 4 and 12. We can simplify this down to 16 times 3, which becomes 4 root 3. So 4 root 3 is my geometric mean. If you're questioning what the common ratio would be, what are we multiplying by in this sequence, you could divide the second term, 4 root 3, divided by the first term, 4, and you would get a common ratio of 3. And that works because 4 times the square root of 3 is 4 root 3. If I multiply 4 root 3 times the square root of 3, I end up with 4 root 9, which becomes 4 times 3, which becomes 12. So you can see how it fits the pattern and it fits our sequence. So now flip over your notes, and I'd like to have you try the problems on the back side. The best thing you can do is just read through them and see if you can apply these concepts to those problems, and then I'll have them in front of you and we'll go over them together. I believe what I'm going to do is create a second video so these don't become too long. So this wraps up the first video of 9.3, and then you flip over your notes to the back side and then see if you can come up with the answers, and then look at the second video to come up with your solutions. Thank you.